Good afternoon, my dear students. Myself, Dr. Girish Chetinelli, Associate Professor, Department of First Year Engineering, Srimati Kamala and Shri Venkappa, I am Agadi Engineering College of Technology and Lakshmisha. Today we are here to discuss about topological indices, its significant types and investigation of few degree-based topological indices and its application. Throughout my presentation, I am going to deal with it's my presentation. I am going to deal with introduction, degree-based topological indices, distance-based topological indices, investigation of few degree-based topological indices, and application. Okay. The development of graph theory is very similar to the development of probability theory. As we all know, graph is a very convenient way to represent the relationship of objects. Here we consider objects as a vertices and relationship of objects as its edges. It has motivated lot of original work was carried out with the help of chance of game theory. Topological indices is nothing but it's a numerical molecular structure which is associated with chemical constitution and chemical correlation of molecules, which helps us to find out chemical reactions, physical properties and biological activity. In general, we can easily say that topological indices are the numerical value or simply value which are associated with the molecule, which helps us to predict physiochemical properties of respective molecule. Here we have a simple molecule. Okay, simple molecule we have, and its molecular graph will be like this. Okay, so and it is converted to a TI. TI is nothing but topological indices. It is simply a number, a numerical number which may be real or which may be positive or which may be negative. This number is associated with the respective molecule, and with that we can easily find out the physical properties, chemical reaction and biological activities of a given molecule. Nowadays, topological indices plays an important role as well as vital role in the study of QSAR and QSPR studies. QSAR means quality to structure activity relationship and quality to structure property relationship. Topological indices are simply numbers that describes graph characteristics which are very useful in the study of chemical graph theory. There are few examples of topological indices. The first topological indices is introduced by chemist Harare Weiner in the year 1947. When he was interested to study about boiling point of an alkane, he used the mathematical model. There he found the first topological index called Weiner index. Second index is Zagreb indices, which was introduced by Beckman in the year 1972. These indices are useful in calculating the total pi electron energy. Similarly, Randic index, which was introduced by Randic in the year 1975, and which helps us to find out regularity and degree of the nodes of molecular graphs. Like that, till now we have more than 1000, approximately 3000 plus topological indices have been open for study. Okay, these are the types we have. Based on their significance, we have divided two significant types of topological indices. First one is degree-based topological indices. Second one is distance-based topological indices. Degree-based topological indices. Here, in this degree-based topological indices, we commonly concentrate on degree of the vertex of the given graph. Then what is degree of the vertex? Degree of the vertex is first neighbor of the vertex in the same graph. Similarly, distance-based topological indices, where we are dealing with distance of vertices along with the edges in the given graph. So based on the study, we got common definition for TI. TI means topological indices of the graph G in the form TIG, topological indices of a given graph G, is equals to summation over UV belongs to G, F of, it's a product of degree du and degree V, degree U and degree V, where G represents, it's a combination of vertices and edges, and which is simple, undirected and connected graph. The oldest and most famous degree-based topological indices are the first and second Zagreb indices. The first Zagreb indice is nothing but summation over a degree of each vertices. That means sum of squares of degrees of each vertices. And the second Zagreb indice is nothing but it's a sum of product of degree of the vertices and edges. So here I have taken simple graph which contains 6 vertices along with the central vertex. Here we are interested to find out the first Zagreb indices of the given graph, and we have a formula. The first Zagreb index is obtained, that is summation over sum of squares of degrees of each vertices. Here look at this vertex V1, it is associated. As I mentioned, degree of vertex V1 is first neighbor of the vertex, number of first neighbor of the vertex. The number of first neighbor of the vertex is V, so degree of V1 is 1 here. Like that, degree of V2 is 1, degree of V3 1, degree of V4 1, degree of V5 1, degree of V6 1, and degree of V is 1, 2, 3, 4, 5, 6. So degree of V are 6 here. Using the same formula, summation over degrees of each vertices, we substituted 1 square because I made clear statement that degree of V1, V2, V3, V4, V5, V6 are 1, where degree of V is 6. Summing all those terms, I got the first Zagreb index is 42, and this is the topological index which is associated with the same molecule, which helps us to predict physiochemical properties of respective molecule. Similarly, this is the second Zagreb index. The second Zagreb index, we have a formula, summation over product of degrees of vertices and edges. So here we can write down degree of V1 into V, degree of V2 into V, till degree of V6 into degree of V. As I mentioned, degree of V1 is 1, degree of V2 is 1, degree of V is 6. Using all those, we are able to find out the first and second Zagreb index of simple graph. Undirected simple graph, we got M1G as 42, M2G as 36. Okay. Next, distance based topological indices. The most popular and the oldest TI, that is topological indices, is the Wiener index of a graph G having vertex set V1, V2, V3 up to Vn, is defined as sum of the distances between all unordered pairs of vertices G. And we have a formula W of G, that is Wiener index G, is summation over where 1 less than or equals to I less than or equals to J. I and J stands for number of vertices and edges. So degree of Vi comma degree of Vj. And we have a formula, and the same thing, it again depends on degree. So we use degree of V1 to Vi. That means here I made a clear statement, distance between all unordered pairs of vertices. Clearly, when we are finding here V1, here we have V. Okay, so this, and I have written here degree of V1 to Vi, and Vi means V1, V2, V3, V4, V6, V5 and V. When I am writing degree of V1 to Vi, here I am writing here. So degree of V1 to Vi. That means when I am writing degree of V1 to Vi, I am writing I is not equals to 1. When I is not equals to 1, I can write down degree of V1 to except V1, degree of V1 to V2, degree of V1 to V3, degree of V1 to V4, degree of V1 to V5, degree of V1 to V6, and degree of V1 to V. Similarly, when I am interested to find out degree of V2 to Vi, degree of V2 to Vi, I am using I is not equals to 1 and 2. Then degree of V2 with V3, V2 with V4, V2 with V5, V2 with V6, and V2 with V. When I am finding degree of V3 to Vi, I am using I not equal to 1, 2, 3. That means V3 to V4, V3 to V5, V3 to V6. Similarly, when I'm interested to find out degree of V4 to Vi, I'm using I is not equal to 1, 2, 3, comma 4. Then V4 is directly V5 and V6. Similarly, D of V6 to Vi. So D of V6 to Vi, I am using I is not equal to 1, 2, 3, 4, 5, then obviously V6 to V. After substituting all the values, we are able to find out Wiener index of the given graph. W of G is equals to 36. So this is distance based topological index. We took Jagraf indices example for the same graph, that is degree based, and this is Wiener index, which is distance based topological indices. Now, one more distance based topological indices is eccentric connectivity index. It purely depends on adjacency. That means it again, adjacency means adjacency come distance based topological indices. It defined as ECIFG, given graph G. Here also I have taken simple graph just for understanding purpose with a small graph. ECIFG, sum over vertex set V of G. It is product of summation over V of vertex set V of G, product of eccentric and degree of the same vertex. So here I have written G, V1, V2, V3, V4 of the vertices of the graph. E of V1. E of V1 stands for eccentricity of V1. E of V2, E of V3, E of V4, degree of V1, V2, V3, V4. Before going to discuss, find out about eccentricity of V1, let me know what is eccentricity. Eccentricity is the largest distance between U, V. Here I am interested to find out eccentricity of V1, then I am interested to find out the largest distance from V1 to other vertices in the graph. The largest distance from V1 to other vertices in the graph. Okay, the distance between V1 and other vertices. So here I am writing distance of V1, V2 is 1. Distance from V1 to V2 is 1. Distance from V1 to V3 is 2. Distance from V1 to V4 is 2 again. Distance of V1 to V2 is 1. Distance of V1 to V3 is 2. Distance of V1 to V4 is again 2. So from distance from V1 to V2 is 1, V1 to V3 is 2, V1 to V4 is 2. Among all these three, which one is the largest? Obviously, degree of distance of V1 to V4 is 2. So here, the largest distance from V1 to other vertices is 2. Then I can write down eccentricity of V1 is 2 here. So eccentricity of V1 is 2. Similarly, eccentricity of V2 is 1 because the largest distance from V2 to V1 is 1, V2 to V3 is 1, V2 to V4 is 1. So eccentricity of V2 is 1. And then eccentricity of V3. The largest distance from V3 to V2 is 1, where V3 to V1 is 2. V3 to V4 is 1. V3 to V4 is 1. So eccentricity of V3 is 2. Similarly, eccentricity of V4 is 2 because the largest distance from V4 to V1 is 2. So now we are able to find out eccentricity, and already I have explained in the previous session the degree of V1 is how it can be evaluated, the first number of first neighbor. So degree of V1 is 1, degree of V2 1, 2, 3, degree of V3 is 1, 2, degree of V4 is 1, 2. So substituting all the eccentricity and degree of the each vertex in the given formula, that is product of eccentricity and degree of the respective vertex. So E of V1, degree of V1, E of V2, degree of V2, E of V3, degree of V3, E of V4, degree of V4, E of V5, degree of E of V4, degree of V4, like that. After substituting all the values, we met with EC of G is equal to 13. It is again a number. As we mentioned, topological indices is a numerical value which helps us to predict physical and chemical properties of the given molecule. Now, investigation. To investigate a degree-based topological indices for large graphs, we have to follow 4 steps. The first step is finding the order and the degree of the given graph. So here we can use order stands for number of vertices, size stands for number of edges in the given graph. Second one, noticing how many vertices with respect to degree, how many vertices how many types of vertices with respect to degree and find their cardinalities. Third one, partition of edge set into subsets with respect to their degrees of end vertices of each edge, as well as investigating their cardinality. And last one is use the above information into the definition of TI, and after simple calculation we have the answer. So we have 4 steps. The first step is finding the order and size of graph. Second one is noticing how many types of vertices with respect to degree and find their cardinalities. Third one is partition of a edge set into subsets with respect to the degrees of end vertices and finding the respective cardinalities. Fourth one, using all the information whatever we have observed from first step to third step in the definition of topological indices, and let's see the simple calculation leads to the answer. Now, here I have taken simple graph, cycle graph Cn, where n greater than or equal to 3. So I can consider when n greater than or equal to 3, it is a large graph. So here we are denoted C3, it has 3 vertices, C4, 4 vertices, C5, C6 and so on. Okay, this is the cycle graph where number of vertices are 3. So I have written n equal to 3. Number of edges are, number of vertices and number of edges are written. Same here, number of vertices, and this can be obtained by writing in general formula for next step. Okay, here I am interested in the first, second and third step. We got 4 vertices, 1, V1, V2, V3. You can start with your V1, V2, V3, V4, dash up to Vn. Here number of vertices are n vertices. Number of vertices are n vertices. When number of vertices are n, then obviously number of edges are also n. Okay, so we got order as n, size as n equal to n. That means order n equal to number of vertices and size n equal to m, number of edges. Then degree of each vertex and their cardinality, that is the second step. Here I have a V1. Okay, so V1, V2, V3, V4, Vn. V1, V2, V3, V4, Vn, dot up to Vn. So degree of V1 is 2 here because it is connected with 2 edges. Degree of V2 is 2 is again, degree of V3 is 2, degree of V4 is 2, degree of Vn is 2. That means the degree of all Vi is equal to 2. And their frequency, how many vertices are there? N frequencies, how many n vertices, and the occurrence of vertices is n. So I am writing frequency equals to 1. Similarly, the degree of vertex, u I am using as vertex, the degree of vertex is 2 and it is connected by 2 edges. So I am writing 2 comma 2. So I am writing 2 comma 2. So degree of u comma degree of v is 2 comma 2, where we have each vertex having degree 2, each vertex connected by 2 edges. So degree of v will be 2. So 2 comma 2 appear m equal to n. Similarly, okay, now the first diagram index of same cycle graph. The first diagram index of same cycle graph. Okay, that is nothing but a formula we have already. M1 of C1 equal to summation u comma u belongs to vertex set V, degree of each vertex. Degree of each vertex. Okay, we'll continue in next class. Thank you.
Thank you one and all.